Hello, 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 Gen Chem 1. We are getting close to the end of Unit 3. We've just got 2 videos left, and both of them will be for double displacement reactions. These are our most complicated. They're a little bit sassy. We've just got the most stuff in our double displacement reactions, so we kind of saved the best for last. So before you start this video, you definitely want the class handouts. You're going to need a solubility table. We're also going to need our naming, like we've already needed. We shouldn't need math, but we're going to follow our same process we've been following in our other videos. So you shouldn't need your calculator, but you definitely need your solubility table. And I put one up on your Blackboard. You can also, Google one, and you'll probably find a million of them. You can notice I put some links in here just in case you want to check out any of these. I've got several links I just kind of posted in here if you don't have a textbook. I'm going to make my way through these, and I'm going to have some language that I'm a little bit particular about. So you'll find some more examples online, but I'm also going to add a little bit to this section and what we're looking at for our double displacement reactions. So let's work our way through them. I'm really excited. They're really similar to our single displacement reactions. That was our last video. But of course, we've just added a little bit of sass to them. So let's work our way through. I wrote out a nice example just to start with. This is kind of a classic double displacement reaction. And I'd like to go through our process. We already have a process, write your formulas. Well, I was really nice and actually started this one with your formulas, but don't worry. Our next example is all names. What? All right, so let's start this one with our formulas already done. And then number 2, we have trust issues. So remember, you've got to find your balance. So we need to balance this. And let's take a look at it. If I'm not mistaken, I think I just went easy on you on this one too, and it's already balanced. I love it. All right, what's number 3? Let's write out our oxidation numbers. All right, of course, if we were going from names, we'd already have a bunch of oxidation numbers written, but since I gave us the formulas on this one, let's go ahead and write some oxidation numbers. So silver nitrate, how would we put that together? Grab your periodic table. Silver is going to be a +1. In fact, I think I'm going to write this out bigger. It's a little bit easier when we do our oxidation numbers if it's just a little bit bigger. And we've seen some of these already, but it really doesn't hurt to repeat it. So let's do our nitrate. Okay, there we go. All right, let's add some oxidation numbers. We'll start here with silver. It's going to be a +1. Our whole nitrate, find that on your common anions. We're definitely going to need that for this video. So our nitrate overall is a -1, but we've learned in a couple previous videos, we're not satisfied with just that. We also write out our oxidation numbers inside those common anions. Sometimes they change. Sometimes they don't. So it's good practice. Let's just write them out anyway. All right, so we start with oxygen. It's the most electronegative. That is going to follow the rules. That's -2. Now remember, we have to add up to a -1. So what does nitrogen have to be? It's got to be a +5. Okay, I love it. All right, our sodium chloride, oh my gosh, could we not do that in our sleep? We've seen it so many times. And then how about our silver chloride? That is going to be the same. And then our sodium nitrate overall, -1. All right, let's fill out what's inside there. -2 for that oxygen, +5 for that nitrogen. All right, so now we can tackle that question of redox. Is this a redox reaction? All right, let's check. On our reactant side, our oxidation numbers did not change. On our product side, this is not a redox. In fact, this is really important. Our double displacement reactions are never redox. They will not go together. You can always double check if you have a double displacement reaction. It will not be a redox. So you can double check yourself when you're writing your structures and your formulas Your oxidation numbers should not change. These will never be a redox. Now, these look a little bit more complicated, but let's break it down just a little bit. It's almost like your silver and your sodium just switch partners. All right, so this is kind of like, hey, we're in Texas. This is like a little do-si-do. Didn't you have to do that in gym class when you were young? We are switching partners in this one. So your silver and your sodium, your two plus sides, look at our cations here. They are literally switching partners. So if we want to write that out in general, you'll notice that our double displacements always follow that same kind of process, and we end up switching those partners. So if you want to write that down as a general scheme of your double displacements, there you go. All right, so let's pause for a second. Why in the Sam heck would that even happen? You have got two partners switching. Why? In our redox reactions, you could kind of see why that might happen. You've got electrons flowing, you've got different strengths with Mother Nature and our elements, but in a double displacement reaction, your oxidation numbers aren't changing at all. You're not getting to something more stable by changing an oxidation number. You don't have electrons flowing back and forth. So really, our double displacement reactions are completely different. We have to figure out a reason for them to happen. Otherwise, they're just not going to happen. They're just going to sit and stare at you. So we're going to look at classic double displacement reactions. And the first thing I'm going to add to this, I'm still in my highlighter, hang on. First thing I'm going to add to this is that in our classic double displacement reactions that we are going to look at in this class, we will consider all of them in water. Okay, that's number one. If you had gotten to this experiment in lab already, you did your calcium carbonate experiment where you made calcium carbonate. You took one flask and you dissolved your reagent in water, your second flask and dissolved your reagent in water, and then you mixed them. All of our double displacement reactions for this class, we will consider all of them in water. And that's going to reflect how we write them out. This is why they're a little bit more complicated. And then second, we are going to look for a driving force. Now that's what I'm going to call it, because in theory, all double displacement reactions are one massive equilibrium. So if you literally don't have a driving force, you're just going to dissolve all this stuff in water and it's just going to sit there and stare at you. Nothing's going to happen. But if we have a driving force, then we're actually not in equilibrium anymore. It's called Le Chatelier principle, and you're going to hit it in Chem 2. You are going to drive your reaction forward. And that's what we're looking for. We're looking for our driving force. And that is going to come from Le Chatelier principle. And I'm not going to test you on the Chatelier principle. You'll get that plenty in Gen Chem 2. I know you're all chem majors by now because you're so excited by chemistry. So our driving forces we're going to look for. Now this language is going to be different sometimes than what you see online. I hate this section in textbooks and online sometimes because everybody views it as a memorization thing. It's not at all. These are equilibrium processes. If they didn't have a driving force, and our driving force is the reason that this process even happens. So what we're looking for is a driving force. How are we going to spot it? There are three main driving forces that are the most common. The first one is the formation of a solid or a precipitate. And that will be on the product side. Your driving forces are always on the product side. Okay, and how do we mark a precipitate? They tend to abbreviate PPT for a precipitate. And I'm going to teach you how we're going to find if we have a precipitate. But why would a precipitate matter? In fact, this is one of the most common driving forces for double displacement. If you've got everything in solution, and it is mixing around, the second you form a precipitate, it falls out of that solution. It has just removed itself from the actual reaction. Well, this Mother Nature will correct itself and make more. So Le Chatelier principle is actually Mother Nature balancing that whole setup, where if you have a product and it's removed from your solution, Mother Nature is going to make another one. Equilibriums are all in a balancing act. And as soon as you remove something, Mother Nature makes another one and makes another one and makes another one, which is why then this process even works, because Mother Nature will keep making whatever is being removed. And if you form a precipitate, you've just removed that precipitate from the solution. So that's our most common driving force, and I'll teach you how to look for that. Number 2, we will look for gases. Okay, if you've got bubbles and you form a gas, it's removing itself from the reaction. You are bubbling out one of your products. And of course, that's the same as your precipitate, just the other direction. You are bubbling out of solution instead of falling out of solution. And then number 3 is a little bit trickier to see. That we're going to save for our next video, and that is the formation of water. Okay, now one of the things to think about is that water is the solvent in these solutions. And when we start to draw them out, I think we'll get a clearer picture of why water can be a driving force. But like I said, we're going to focus on the first 2 driving forces in this video. And then in our next video, we're going to tackle the water. All right, so what do we do with these things? They're obviously bigger, they're more complicated, and we have to look for something called a driving force. How do you even start? Where do you know where a driving force is? So this is where we grab our solubility table. Since everything in this reaction is in water, the first thing we're going to do is add more information to this reaction. Remember, every reaction is one big story. We are just adding to that story. So let me erase some of this, so screenshot if you need to, and let's start adding some more detail to our reactions. All right, so step number 1 is to find everything on a solubility table. We are going to write our double displacement reactions in 3 different ways. This first way is called our formula unit. This is the most common. But for double displacement reactions, we need to literally picture what they're going to look like in the lab in water. That will help us find our driving force. And that's going to help us picture what these reactions look like in the lab. So we will also write them in something called a total ionic equation, and then finally a net ionic equation. So make sure you've got your colored pencils and a lot of paper, because we are going to write these out big. All right, so grab your solubility table and let's start adding some information. We've got to add one more piece of information before we can write out these 3 sets. So I'm going to grab my solubility table and I'm going to look for silver nitrate. And I'm going to read, let's see, silver, I've got it on the up and down side for silver. I'm going to read over to nitrate. And I'm going to find that my solubility is marked at AQ for aqueous. It dissolves in water. Yours might say soluble in water. It just depends on your table. Both of them mean the same thing. We mark it AQ. They are aqueous. They dissolve in water. So if you take silver nitrate and you throw it in water, it's going to dissolve. All right, let's read your sodium chloride on your solubility table. And what do you find? You're going to find that that is aqueous as well. Okay. All right, let's find silver chloride. I'm reading over silver to chloride. Look at that. My solubility table has it marked as an S. That is for solid. Let's mark that S. That means that does not dissolve in water. So if your solubility table is telling you insoluble, you're going to mark that with a solid. That means this is a precipitate. As soon as you form silver chloride, it falls out of solution. All right, if you're with me so far, isn't that a big indicator right there? That is going to be our driving force. Okay, and then our silver nitrate, let's see if we've got two driving forces. Let's see. Silver nitrate I am finding is aqueous. Okay, deal. All right, now let's write the 4. We just wrote the formula unit. That's the first one. Let's write total ionic and net ionic equation. And they both have a different purpose. Our total ionic equation is specifically for us to envision in lab what this reaction looks like. So I'm going to put brackets around it, and I'm literally going to take silver nitrate and dissolve it in water. All right, now we're going to use a trick from Unit 2. I'm going to ask you to picture Unit 2, and I'm going to ask you what bonds here are ionic and covalent. Your bond to silver is ionic. Your bonds between your nitrogen and oxygen are covalent. When you dissolve in water, you break the ionic bond and you leave the covalent bond alone. All right, so let me show you what that looks like. What does that mean? That means that if I take silver nitrate and I put it in water, silver as an ion is now free floating. It is no longer bonded to nitrate, and it is floating around in water. Now, this is not elemental silver. This is silver that has already lost its electron. So you have to put the charges in, and you have to mark that it's soluble in water. The most commonest mistake, don't you love it? It's not an English class. My most common mistake on this next test is to forget to label those things. They are crucial. Again, that is not elemental silver. That is the ion of silver. So you have to have that label. All right, and then it is floating around. So is our nitrate. That whole nitrate as a -1 is free floating, but your nitrogen and oxygen is stuck together. You've drawn that structure in Unit 2. That is a free floater, but your molecule is still stuck together, but the ion is now free floating. All right, so let's do the same thing for sodium chloride. All right, break the ionic bond. That means you've got a silver or a sodium floating around, and that is aqueous. And you've got your chloride floating around. Oh, shoot, sorry, y'all. And you've got your chloride floating around, aqueous, okay? So then we put a bracket around that. That is what your entire reactant side looks like. You're going to dissolve these two, put them in a beaker, they're in water. Take these two, dissolve them in water, put them in another beaker, okay? You would look like water and water right there, all dissolved. Then you would mix them together. And I'm going to have to write that down on the bottom. And the second you pour those together, what is it going to look like? All right, let's envision. You've got silver floating around, and it is smacking into nitrate. Well, who cares? Because that bond breaks again, and it's free floating again. Your silver smacks into a chlorine. Now those two smack into each other, and what just happened? You just formed the bond between silver and chloride. They are no longer just floating around. They have now formed that precipitate that falls to the bottom of your flask. So those two ions right here have just removed themselves from the reaction. So we don't put them in brackets and you leave that bond together and they are a solid. So then what is still floating around in your solution? What's left behind? Well, you still have sodium and you still have nitrate. They are still free floating, and it doesn't matter if they smack into each other because they're just going to break again. That bond is going to break. Just like if a nitrate smacks into a silver, doesn't matter, that bond just breaks again because they're soluble in water. The one that doesn't break again is our driving force. That is our sodium chloride, and that is what makes that reaction happen. As soon as those two atoms form that molecule and they fall out of solution, Mother Nature is going to make another one and make another one and make another one. And that's what makes that our driving force. So what do we call the sodium and the nitrate then? Those are spectator ions. All right, why do we give a crap about this, and why do we list these all out like we were in lab? Well, let's picture it this way. You're in lab, you mix them together. This just made a precipitate and it's out of solution. It looks like a snow globe in your flask right now. This is still in your solution. So how are you going to isolate this one versus this one? You filter it. That's it. It's like making coffee. So if you were to filter this reaction, which if you did this experiment in lab, you would filter this. Aha, this is the product you isolate. This ends up in your waste. So that's why we picture it that way. Would this be a great reaction if you wanted to make silver chloride and isolate it? Absolutely. Would this be a good reaction if you wanted to make sodium nitrate? Maybe. You'd have to take another step and dry it. You'd have to find a way to isolate it from your waste. You'd have to remove the water from it. So that's why we picture it that way. And then we take the next step and we draw just the driving force. And that is called the net ionic equation, because typically in these reactions, that's what you're going to isolate in the lab. So for our net ionic equation, then what we draw is literally just what makes your driving force. So we are going to have that silver and that chloride, and when they smack together, they're going to make silver chloride. So let's add our details. So your net ionic equation is just your driving force only. Okay, awesome. All right, this is a whole lot of detail just for one reaction. So I feel like we need to turn right around and do this again. This is so much fun. Let's do it again. Oh, what? Shut the front door. Did I give you names? Don't you love chemistry? So grab your common anions and grab your solubility table. Let's see how much information we can add to this reaction. Let's start all the way back at the front, at the top of our list, and let's add our formulas. Let's figure out our barium. Whoa, what did I just do? All right, let's figure out our barium chloride. And how do we do that? BaCl. We need our oxidation numbers. Barium is a +2. Cl is a -1. Okay, I love it. Sodium and sulfate. Grab your common anion sheet. Sulfate is a -2. Sodium is a +1. So we need 2 of them. Okay, let's take our barium and our sulfate. That is a +2. This whole thing is a -2. All right, we're good then. We're set. And then sodium chloride. We've already seen that. All right, deal. All right, let's add some more information. Why not? This is good practice. So let's double check. Let's check our balance, What do we need to do to balance this one? I kind of feel like we need to add a 2 there, and then we're going to be balanced. Okay, I think that works. And then let's go ahead and add the additional oxidation numbers, and let's just see if this is a redox reaction. I'm going to add, we've done sulfate in an earlier video, so I'm going to go ahead and add that in. Okay, is this a redox reaction? No. And is this a double displacement reaction? Did your plus sides just change partners? Did they get bored and decide to change partners? Yes. Okay, so this is now not a redox. It is a double displacement reaction. So let's reach for our solubility table. We've got another step in our process. So we basically had to write out our formulas, and then we had to balance. And then we added our oxidation numbers, and now we're grabbing our solubility. And we're going to add whether or not something is a solid or aqueous. Okay, perfect. I love it. All right, grab your solubility table. Let's look for barium chloride. I'm going to grab my table and let's see what we've got. Barium, and I look over at chloride and I see that it is aqueous. Okay. Sodium sulfate, I see that that is aqueous. Barium sulfate, let's double check. Son of a motherless goat, that is a solid. And our sodium chloride, aqueous. All right, I love it. Did we not just spot our driving force? We did. That barium sulfate, that is going to be our driving force. Okay, now we're ready to write the total ionic equation and the net ionic equation. All right, I love it. I'm going to draw my brackets. Now, barium chloride is aqueous. Break the ionic bond. So barium and chloride are going to be separate. Don't forget your labels. That is not just elemental barium, that is the ion. You have to put that in there. That is not chlorine, toxic gas, Cl2, that is chloride ion, common in your body. Okay? Our sodium sulfate, that is aqueous. Break the ionic bond, so that means our common anion, that SO4, sulfur and oxygen, have a covalent bond. Keep that crap together. Keep it together, you guys. Just keep it together. All right? And that is a -2. And now you break those bonds to sodium. All right, wait for it. This is going to be fun. All right, but you don't have one of them. You have 2 of those sodiums. They are both a +1, and they are aqueous. Okay, so now this is what your reactant side is going to look like. You've got those in water in 2 separate beakers. You dump them together, and what happens? A barium smacks into a chloride. Doesn't matter, the bond breaks again. Barium smacks into sulfate. Aha! And now it matters because that bond does not break again. That is your solid. That is your driving force, and that forms a precipitate. Do you need to put your charges there? You can. You can. I am always a fan of charges. I never say no to charges. And then what else is left in your solution? You still have the sodium and the chloride, and they are still floating around in that solution. So why do we care? Well, if you're doing this reaction in the lab, you're going to isolate the barium sulfate, you're going to filter it, and then in your waste is going to be your sodium chloride. Those are your spectator ions, those are your floaters. Okay. I love it. All right, so now what do we combine to write our net ionic equation? Whatever it takes to make the barium sulfate. Remember, that's your driving force. So our net ionic equation, this was our total ionic equation. Our net ionic equation is just our barium and sulfate, making that barium sulfate. Oh, I just did the wrong charge on barium. Do not do that. Okay. And then these are aqueous. And this is a solid. Okay, I love it. I love it. But I feel like we need to do one more of these. These are a lot of information. They're big. All right, both of these two are a perfect example of a precipitate as a driving force. I want to do one more, and that's going to have a little bit different driving force. And we can pick up the pace just a little bit with this one. I'm going to write out this potassium sulfide. How do we put that together? Like that. And then hydrogen chloride. There we go. I'm going to go ahead and add oxidation numbers because we know we're going to look at it for redox anyway. All right. And then our potassium chloride, let's double check those. And then our dihydrogen sulfide. Okay. And so just for funsies, because we're going to look at it for redox, I added those numbers. All right, let's see. Are we balanced here? I don't think so, right? I think we're going to need a 2 here and a 2 here. Okay, I love that. That looks pretty. Okay, now let's add to our process. Let's grab our solubility table and let's see if this stuff is on there. You may have to Google some if your solubility table isn't big enough, but I'm noticing that I have it on there so I can give it away for free. This potassium sulfide is aqueous. Oh, this one isn't on there. What? This is foreshadowing. This is our next video. Our HCl we're going to learn is an acid. So I'm going to give this one away for free. Some of your solubility tables will have a hydrogen on it. Some of them won't. I'm going to give it away and tell you that we'll mark that aqueous. Okay, and we're going to put a little sparkle pen on here. That's our next video. I love it. All right, then on our potassium chloride, that one is aqueous. Okay, now we have 2 things going on here. H2S, what kind of bond is that? Ionic or covalent? Well, son of a motherless goat, that is covalent. And we were told to break the ionic bonds. That's what makes your hydrogen chloride weird. But I already told you that's a cliffhanger for the next video. But this covalent bond, that's not going to break again in water. And it turns out that this is a gas. Okay, now I wouldn't expect you to know your gases. So let me give you a list of some of the common gases. You know, some of our elements in their elemental form, we know that those are gases. But what are some of our common gases molecules that we could make? Any of the NO derivatives, so you can have NO, you could have N2O, you can have N2O4, you could have NO2. Any of those NO derivatives, they're all gases. Our sulfurs are gases. Some of those are gases. These are some of our common gases. So maybe write those down on your cheat sheet. If we end up making some of those are going to be our gases. All right, once we spot the fact that we just made a gas, that's our driving force. So how do we write this reaction out? Same as the other one. We're going to take our total ionic equation. Okay. All right, our K2S, our potassium sulfide, let's spell that out. And I'm going to write in blue first, and then I'm going to come back in and add my labels. Now, what makes HCl an acid, we'll learn in the next video, is that it does break apart in water. Okay, so let's add our details. Let's add our charges. We cannot forget those. And then let's add the fact that these are all aqueous. And then remember, we've got 2 of these and 2 of these. Okay. Oh, and 2 of these. I love it. All right, now let's make our products. So that KCl, that's still broken apart. Those are our spectator ions. So let's add these in there. Let's add our charges. We've got 2 of them, and they are both aqueous. And then we're going to make that H2S and keep it together. Keep that one together. That came out bad, is a gas, and we mark that with a little G. I love it. So then what is our net ionic equation? Well, those H's and S to make that dihydrogen sulfide, which is a gas. All right, so let's add in our labels here. And that is our net ionic equation. And then what would be our spectator ions? Our KCl are going to be our spectator ions. Okay, I love it. All right, this video got a little long because there's so much detail in these reactions, but now we've done 3 double displacements, and we've done 2 precipitates. You need your solubility table, and we've done a gas forming. And so now I'm gonna put up another video. We're gonna do a couple more examples, and they will all be driving force of forming water, and they are going to include the acids and